Hello everyone, my name is Lin. Today I would like to share our recent work, SPG, Structured Private Graph Database via SqueezePIR. Currently, graph neural network is widely applied in many applications, such as recommendation system, fraud detection, and traffic monitoring. As the data size increasing, the entire graph can reach TB level in industry. Thus, people would like to move the entire graph on the cloud side and perform inference on the edge. However, graph data may expose personal information. Thus, in this work, we mainly consider how to keep the graph private under the cloud service scenario. Now, let's look at a concrete example of the graph service framework. The server side stores the edge list and feature list. Edge list stores the neighbor node's ID for each node, and feature list stores the feature of each node. In this framework, the client will first retrieve neighbor node's ID from the edge list and then retrieve the corresponding features from the feature list. Then, based on the retrieved feature, client can perform graph neural network locally. Based on this process, we will first identify the privacy issue in this framework. In this framework, the server is entrusted. We may face two kinds of privacy issues. First is data privacy. We don't want to expose the data content to the server. It can be easily solved by encrypted data. Another kind of security issue is the structure privacy of the graph. Since during the feature retrieving, the retrieving index may reflect the neighbor node's ID and then expose the connection information of the graph. Thus, in this work, we mainly consider how to protect the structure information of a graph under a cloud service framework. A widely used technique to hide the retrieving index in the database service is called private information retrieving. In this work, our design framework is based on this protocol. Now let's first take a look at what is PIR. When a client retrieves a record from the server, PIR can help to prevent the retrieving index learned by the entrusted server. As the figure shows here, the server stores the database as a matrix. Each row represents a record. During the retrieving, the client needs to first generate a one-hot vector. This vector encodes the index of the record that wants to be retrieved by the client. Next, the query is encrypted into ciphertext and sent to the server. In the third step, the server computes the desired record through the encrypted query. The computation in this step is based on homomorphic encryption. Thus, all data are in ciphertext and no information is exposed to the server. Then the computed result will send back to the client. And finally, the client can recover the original data through its secret key. In PIR, the most time-consuming part is the computation on the server. Currently, FastPIR is one of the state-of-the-art PIR protocol. The key idea can be illustrated as the following flow. In the beginning, the database will be slicing into several columns according to the parameters of HE protocol. The query is batch encrypted into a vector. The encrypted query performs homomorphic element-wise multiplication with each column of the database to select the desired record. In the end, the data in different columns is reduced into one ciphertext through homomorphic rotation and addition. Now, let's look at how to apply PIR on graph processing. Note that the edge list and feature list are stored on the server. Client needs to first retrieve neighbor node's ID from the edge list, and then retrieve features from the feature list based on the neighbor node's ID. These two rounds retrieving are all realized through PIR. Based on the profiling, we find that the feature retrieving is much slower since the node's feature size is far larger than the node's ID size. Thus, in this work, we mainly focus on how to accelerate the feature retrieving. Now let's go through the opportunities and challenges. For most of GNN algorithms, we can tolerate some noise in the node feature. This noise has limited impact on the accuracy. Thus, we can apply low-rank decomposition on the feature list. However, after the database is decomposed, existing PIR protocols cannot be directly applied, and existing HE protocols for matrix multiplication will cause huge performance degradation. In this work, we designed SqueezePIR, a protocol that optimizes the PIR processing on the decomposed database with limited overhead. Now let's go through the detail of our protocol. In the beginning, the database can be viewed as a 2D matrix. Each row represents a record. Then the database is partitioned into different groups according to the security parameters. Each group contains the same number of rows. In SqueezePIR, each group will be further decomposed through low-rank decomposition. Assume the clients want to retrieve the record in the red box. We can find that the record can be recovered through vector matrix multiplication in the decomposed database. Our SqueezePIR will mainly focus on how to achieve the corresponding vector matrix multiplication under ciphertext efficiently. Before going into the detailed protocol, we would like to first give a background of homomorphic encryption. In this work, we adopt CKKS as the HE scheme. In CKKS, elements are encrypted into a vector as a ciphertext. It can naturally support three homomorphic operations: element-wise addition, element-wise multiplication, and rotation. Our protocol is realized through these three basic operations. Now let's go through the detailed protocol. We use database A and B to represent the two segments of the decomposed database, and we need to pick the data in the red box first. We select the data in database A by applying homomorphic multiplication and addition between query 1 and each column in database A. Here, only one vector in query 1 is a one-hot vector, and other vectors are all zero vectors. In order to select the data in database B, we apply homomorphic multiplication and addition between query 2 and each row in database B. In query 2, the selected group encrypts an O1 vector, and other vectors in query 2 are all zero vectors. Now we have selected the data in database A and B. Before going into the next step, let's first take a look on how the workflow of vector matrix multiplication under plaintext. From the figure shown here, each row in the matrix will multiply with the corresponding scala in the vector, and the intermediate results will be added. However, HE algorithms only support element-wise multiplication between two ciphertexts. In order to accord with the computation pattern, we can expand a scala into length n vector by replicating the scala n times. Under this data structure, the vector multiplication can be achieved by applying element-wise multiplication and element-wise addition between vectors. Now, the data in database B have been extracted under expected form. However, for the selected data in database A, there is only one effective data in each vector. So we need an expansion operation. We achieve the expansion through homomorphic rotation and addition. Note that for each selected vector in database A, the invalid slots encrypts 0. Thus, we adopt a recursive method to realize the expansion, which takes log n complexity. After we acquired the expanded vectors for database A, we can achieve the original vector matrix multiplication through homomorphic multiplication and addition, as the workflow shown below. The computed result will be sent back to the client side, and the client can recover the plaintext through its secret key. Now I will show you the evaluation of our SqueezePIR. we built the protocol based on the SEAL, which is a widely used HE library. The hardware platform is CPU. For HE parameters, the polynomial degree is 8192, and the levels is 4. We evaluate the performance on 4 real-world datasets. We compare our protocol with 3 other baseline methods. We first compare SqueezePIR with other protocols on synthetic datasets. Here we set the rank after decomposition to 512. Based on the evaluation, SqueezePIR achieved 5.5 times and 4.3 times speedup against SealPIR and the naive method on average. Compared to FastPIR and the CKKS encryption, SqueezePIR achieves maximum 3 times speedup. Here, we evaluate the SqueezePIR on real-world graph datasets. We adopt different ranks for the decomposed database, and our baseline is FastPIR and the CKKS encryption. Based on the evaluation, SqueezePIR achieves 2.7 times and 10.1 times and 32.5 times speedup when ranks are 512, 128, and 32 respectively. Usually, we can use the accuracy drop of a graph neural network model as a matrix to determine the rank for each decomposed database. In our evaluation, we assume 2% accuracy drop is acceptable. Based on our evaluation, the SqueezePIR achieves around 12 times speedup compared to FastPIR on average, which makes the feature retrieving time close to the edge retrieving time. In summary, our work first proposed the SPG framework, which is built on top of PIR to prevent the server from learning the graph structure through the retrieving tracks. Then we designed SqueezePIR that can accelerate data retrieving by approximating the database with low-rank decomposition. Based on our evaluation, our SqueezePIR shows an average 11.85 times speedup with less than 2% accuracy drop when compared to FastPIR. That's all of our work. Thanks.